In this video, we are going to determine the roots of a polynomial using a specific theorem called the rational roots theorem. And then we are also going to use a technique developed by Descartes, and his technique is called the rule of signs. To begin, let's look at what the rational zeros theorem actually says. So the rational zeros theorem is really important in factoring polynomials because it allows us to quickly come up with a list of all the possible zeros of a function. So we are going to look at the leading coefficient term, and then we're also going to look at the constant term, and we're going to relate those two things to determine all of the possible rational zeros for a function. So like I said, we want to look at the constant term, meaning the last term of the function, the one without an x term. And then we also want to compare that to the factors of the leading term, the leading coefficient. So as an example, let's look at some function f of x equals 3x squared plus 4x minus 12. Now, in order to determine all the possible rational zeros, we are going to look at the factors of this constant term here. So my 12 is my constant, and we're going to divide it by the factors of my leading term. And my leading term is 3x squared, so I'm going to look just at the coefficient, and I'm going to divide by my factors of 3. Now, the best way to figure out how this works is to look at an example. So here we have the function f of x equals x cubed plus 5x squared minus 4x minus 2. And if we want to totally and completely factor this, maybe in order to graph it, we first need to know the zeros, right? We need to know where the x-intercepts are. This is difficult to factor, right? We can't group it. There's no x term that's common to all of these, so we can't pull that out. So the best thing to do is use the rational zeros theorem. So we know from the previous part of the video that we want to look at the factors of our constant. So in this case, our factor, or our constant term, sorry, is our 2 right here. So we want to look at the factors of 2, and we want to divide by the factors of our leading term coefficient. So since our leading term is x cubed, the coefficient in front of this term is 1. So we want to divide by the factors of 1. All right, now when we're looking at factors, we have to take into account that they're going to be positive and negative. So the factors of 2 are going to be plus or minus 1 and plus or minus 2. That's all we have. Now we want to divide by the factors of 1, the factors of our leading coefficient. So we have factors of 1 is just plus or minus 1. Okay, now we want to look at all the different possibilities we can make with this that we have right here. So we see that I can look at this factor right here. So I have 1 divided by 1, so that gives me plus or minus 1. And then I also have 2 divided by 1, so that gives me plus or minus 2. So in this case, I have 4 possible rational zeros. Now obviously, this is a cubic function, so these are not all my zeros. These are not guaranteed zeros. But according to my theorem, these are the possible ones. So I can test using synthetic division whether or not these are actually factors of my polynomial. The last example, however, that one was too easy. So let's look at something that's going to be a little bit more challenging. So again, we want to use the rational roots theorem, the rational zeros theorem, in order to determine all of the possible zeros, all the possible factors of this polynomial, right? As it is right now, we have no idea what its factors are because there's no techniques that we know that we can use to factor. So again, I'm going to look at the factors of my constant term. So the factors of my constant term, 36, and I want to divide that by the factors of my leading term coefficient. And my leading term coefficient is right here at 2. So I want to compare the factors of 36 to the factors of 2. All right, now 36 has a lot of factors, and we have to list every single one of them. So we start with 1, so we have plus or minus 1. 2 is a factor. 3 is also a factor. 4 is a factor. 6 is a factor. 9 is a factor. 12 is a factor, 18 is a factor, and 36 is a factor. Okay, now we want to divide all of that by factors of 2, and that's just plus or minus 1 and plus or minus 2. Those are only factors of 2. All right, now we do just like what we did in the last example, we can look at how these relate. So we want to take a term from the top and divide it by the term from the bottom and go all the way through. So let's start with the top and divide them all by 1. So here, all the possible factors, we have plus or minus 1 divided by 1, plus or minus 2 divided by 1, and so on. So we have all of these terms here. You can write all of these out. So many possibilities. Okay, now I want to go through and look at with 2 as my denominator. So instead of 1, now I want to look at all the combinations with 2. So that gives me plus or minus 1/2. When I do plus or minus 2 divided by plus or minus 2, that's 1, and I've already listed that, so I don't have to list it again. All right, so going through, I see that the only combinations I have left are these 3 right here. Okay, now I have come up with all the possible rational zeros using my theorem. Again, I'm not going to use all of these. These are not all the zeros of the function because this is only a cubic. And according to rules about a cubic or any type of function, the highest possible number of zeros that you have is your highest degree. So this function, right, this cubic function has a possibility of 3 zeros. All right. The ones we've listed down here, all these, now these are possible, right? But that, again, does not necessarily mean that these are our zeros. Okay, so we have this whole list, but how do we use this to help us factor our polynomial? Well, we have to apply synthetic division in order to do that. Okay, so we have all these options, and basically you just have to start guessing which zero is, or which rational zero you think might be a factor of our polynomial. So the technique that I always use is to start low. Okay, so instead of testing maybe positive 18 in synthetic division, right, that's not necessarily going to get you anything that you want. Start with zeros that are lower. So let's start with positive 1 first. So I'm going to test to see if positive 1 is a zero of my function. So I'm going to put 1 outside here. Since it's a linear term, I can use synthetic division. And I'm going to put my coefficients 2, minus 4, positive 18, negative 36. Now I just go through synthetic division like I know how. So I can bring down this 2. 2 times 1 is 2. This becomes negative 2, 16, 16, negative 20. So because I get a negative 20 here, I get a remainder. I can conclude that 1, or rather the factor x minus 1, is not a factor of my polynomial. So I move on, okay? I could test negative 1, but let's move on to 2. So let's test 2 in the same way. So here I'm going to set 2 as my factor, and I have the same coefficients. And my goal in all of this is to get to a remainder of 0, because according to the factor theorem, remember, if I have a remainder of 0 in this box, then I can conclude that the number, or the c value that I started with, is a factor. So I bring down my 2, so this becomes 2 times 2 is 4, 0, 0, 18, 36, 0. And we've hit the jackpot because we have a remainder of 0. So I can conclude that x minus 2 is indeed a factor of my polynomial. Okay, and I would write that by continuing to expand, just like we have been. So I would say f of x equals x minus 2, and now these are the coefficients of my new function. So I would have 2x squared plus 18. Okay, I could look to see if I can continue factoring this, but when I do that, even though I can pull out a 2, or I could pull out a 2 from here, I'll go ahead and put it in the front here, I would have x squared plus 9, which this cannot be factored anymore because it's not a difference of 2 squares. So this is the fully factored form of my polynomial. I know that I'm going to cross the x-axis at 2, right? It has a multiplicity of 1, so I know I'm going to cross the x-axis there. And that is the only place, even though it's a cubic, I am only going to cross at 2. This right here is going to give me imaginary zeros. So as you just saw, it can be really difficult to test all of the possible zeros. When we, for that last example, we had 24 possible zeros, and even though we got the right zero on the second try, you could go through all of them and then realize at the very end that none of them worked, or the last one you tried worked. And that can be really frustrating. So this guy, Descartes, he was a French mathematician, and he actually makes our life a lot easier when it comes to determining the types of zeros that our polynomial has. So Descartes developed something that we now call the rule of signs. And the rule of signs is examining variations between our original f of x function. And we want to look at it in terms of f of negative x, meaning that for every x that we see, we would substitute in a negative x. And we want to examine the variations between the functions in terms of signs, so S, I, G, and H, moving from positive to negative or negative to positive. And that, the variations in sign, will help us determine how many real positive or how many real negative zeros we have. So in order to determine how many positive zeros we have, we want to look at sign changes. So we see that this first term is negative, this term is positive, this term is negative, this term is negative. So it changes in sign from negative to positive right here, and then at this term from positive to negative again. This third term here, though, negative, stays negative, so that doesn't become a sign change. So because we have two sign changes, we would say that there are 2 or 0 positive rational zeros. Okay? And the reason we say that there's 2 or 0 is we always want to go down in even increments. So if there were 3 sign changes, then I would say there were 3 or 1 positive rational zeros. So you always go down in increments. Don't ask me necessarily why. That is just part of the rule of signs. I'm sure there is a long proof for that, but we will not worry about that right now. So when we're looking at f of x, we're determining sign changes and how that relates to positive zeros. And I misspoke here. I meant to say real. So they don't necessarily have to be rational, but they are real. Now the second one we want to look at is when we substitute negative x into our function. So when we do that, we see that this becomes f of negative x equals negative 3 times negative x cubed plus 2 times negative x squared minus a negative x minus 1. So wherever I see an x in my original function, I'm just substituting in a negative x. Now I can simplify. This is going to make my sign change. So 3x cubed plus 2x squared plus x minus 1. Now I want to look at the sign changes for this function. Okay, so I see that I have a positive to a positive, positive to a positive to a positive to a negative. So from positive to negative, I would mark that as a sign change, and I would conclude that I have one possible negative real zero. So using Descartes' rule of signs, I can narrow my focus for my function. So I can quickly apply the rule of signs, and I know, example for up here, that I have 2 or 0 positive real zeros. So if I find 2, then I don't need to keep searching. I don't need to keep applying synthetic division in order to find more. I have my maximum. Same thing here, right? I know that there might be a negative value, but there's only one. Okay, there's not going to be more than one. So if I found a negative value using synthetic division, I got a remainder of 0, then I don't need to test any more negative values because according to the rule of signs, there's only one possible. So this helps us, it makes our life a lot easier, especially when we have 24 possible zeros that were given to us from the rational roots theorem.